In the summer of 1950, 4 men sat down to lunch at a place called Fuller Lodge. It was in Los Alamos, New Mexico, the same facility where 5 years earlier, the United States had built the first atomic bomb. The men walking to lunch that day were Enrico Fermi, Edward Teller, Emil Konopinski, and Herbert York. All of them had worked on the Manhattan Project. All of them understood, on a level most human beings never will, what it means to build something that cannot be taken back. On the walk over, they had been talking about flying saucers. There had been a rash of UFO sightings that summer, and someone brought up a cartoon from the New Yorker magazine. It was by an artist named Alan Dunn, and it showed little green aliens climbing out of a flying saucer in New York City, stealing trash cans off the street. Konopinski remembered that Fermi laughed at it and said it was a reasonable theory because it explained 2 things at once: the flying saucers and the missing garbage. They sat down. The conversation moved on to other things. And then, according to Edward Teller, right in the middle of an unrelated discussion, Fermi said something that nobody at the table expected. He said, "Where is everybody?" Teller later wrote that the result was general laughter because despite the question coming completely out of nowhere, everyone at the table immediately understood what he meant. He was not asking about the other people in the cafeteria. He was asking about extraterrestrial life. He was asking why, in a universe this large, this old, and this full of stars, there was no evidence that anyone else had ever existed. York remembered it slightly differently. He recalled Fermi saying, "Don't you ever wonder where everybody is?" Konopinski's version was, "But where is everybody?" 3 different men, 3 slightly different phrasings, but the same question. And it is a question that 75 years later, nobody has been able to answer. We know these details because in 1985, a physicist named Eric M. Jones at Los Alamos National Laboratory wrote letters to the 3 surviving participants, asking each of them to recall exactly what was said. Fermi had been dead for 31 years by then. The variations in their memories are instructive. Each man remembered it slightly differently, but remembered the impact identically. It was not a gradual thought that emerged from discussion. It was a bolt, a question that arrived fully formed, as if Fermi had been running the calculation in the background while eating his lunch, and the answer had just come through. And Fermi trusted math more than he trusted assumptions. You have probably heard of this before, the Fermi Paradox. It shows up in popular science videos, in Reddit threads, in late-night conversations when someone has had a few drinks and starts thinking too hard about the size of the universe. And the way it is usually presented goes something like this. The universe is really, really big. There are billions of stars with billions of planets. Some of those planets are probably like Earth, therefore aliens probably exist somewhere. But space is so vast that we just have not bumped into each other yet. That version is wrong. And the reason it is wrong is the part that almost nobody talks about. The Milky Way galaxy contains somewhere between 200 billion and 400 billion stars. Current estimates suggest that roughly 6 billion of those stars have Earth-like planets in their habitable zones. The galaxy is approximately 100,000 light-years across, and it is about 13 billion years old. Those numbers, by themselves, do not tell you much. They are just large. But there is another number, and it is the one that changes everything. In 1975, an astrophysicist named Michael Hart published a paper in the Quarterly Journal of the Royal Astronomical Society. The paper was called An Explanation for the Absence of Extraterrestrials on Earth. And in it, Hart did something deceptively simple. He calculated how long it would take for a single civilization, starting from a single star system, to colonize the entire Milky Way galaxy, not at light speed, not with any exotic physics, just using ships traveling at a fraction of the speed of light, hopping from star to star, establishing a presence in each system before moving on to the next. His answer was a few million years. Think about that for a moment. The galaxy is 13 billion years old. A single civilization, using technology not dramatically more advanced than what we can currently imagine, could spread to every star system in the galaxy in a few million years. That is less than 0.1% of the galaxy's age. It means that if even one civilization anywhere in the galaxy at any point in the last 13 billion years decided to expand, the galaxy should be full, not just occupied in places, full, saturated, every star system touched, catalogued, colonized, or at least visited. And if you think a few million years still sounds like a long time, it gets worse. In 1980, a physicist named Frank Tipler published a paper that made Hart's estimate look conservative. Tipler pointed out that you do not need crude ships hopping from star to star. You do not need biological beings at all. You need one thing, and it is a thing that a mathematician named John von Neumann had already proved was possible 30 years earlier. You need a machine that can copy itself, a self-replicating probe, a machine that lands on an asteroid or a moon, mines the raw materials, builds a copy of itself, and sends that copy to the next star. The copy does the same thing, and the copy of the copy does the same thing. Exponential growth, the same math that describes bacteria in a petri dish, or compound interest, or a nuclear chain reaction. Tipler calculated that with self-replicating probes traveling at less than 1% of the speed of light, and replicating once per star system, the entire Milky Way could be filled in roughly 300 million years. Other researchers later tightened that estimate. Some models put it as low as 4 million years. 4 million years to fill a galaxy that has existed for 13 billion. To put that in perspective, 4 million years ago, our ancestors were Australopithecus, small-brained hominids in East Africa who had not yet learned to make stone tools. The galaxy could have been fully colonized from edge to edge in less time than it took for a primate to develop a brain large enough to wonder about it. If you compressed the entire history of the galaxy into a single calendar year, with the Big Bang on January 1st, a colonization wave of self-replicating probes would sweep the entire Milky Way in roughly the last 3 hours of December 31st. That is how short 4 million years is on a galactic timescale. That is how easily the galaxy should be full. Carl Sagan and William Newman ran their own numbers in 1983, and what they found was even more alarming. They argued that Tipler had actually underestimated the replication rate. Even if each probe produced only a single copy of itself at every stop, the total mass of probes would consume the entire mass of the galaxy within a few million years. Their conclusion was that any civilization wise enough to build such probes would be wise enough not to. Self-replicating machines, Sagan argued, would be the most dangerous technology a species could create, and any rational civilization would ban them. That sounds reassuring until you think about it for more than a few seconds. Sagan's argument only works if every civilization that has ever existed in the history of the galaxy made the same decision. All of them, every single one, across 13 billion years, across hundreds of billions of star systems. Not one outlier, not one rogue state, not one civilization that was desperate or careless or simply did not agree with Carl Sagan about what constituted wisdom. The math does not care about intentions. The math says the galaxy should be full. It should have been full billions of years ago. And when Fermi sat down at that table in 1950 and asked where everybody was, what he was really asking, whether he knew it or not, was why the math was wrong. You were taught that the Fermi Paradox is a question about distance, about the vastness of space, about how hard it is to cross the gulf between stars. It is not. The distances have been accounted for. The timescales have been calculated. The engineering has been analyzed. And what the numbers say is that the gulf between stars is not a barrier. It is an inconvenience. A civilization with self-replicating probes could cross it millions of times over in less time than it took multicellular life to evolve on Earth. The paradox is not about distance. The paradox is about silence. And silence in a galaxy that should be roaring with activity is not a passive observation. It is a data point. It is telling you something. There is a detail that tends to get lost in the popular retellings of the Fermi Paradox, and it is the one that matters most. Earth's atmosphere has contained free oxygen in detectable quantities for approximately 2.4 billion years. That is not a recent development. That is not something that started when we invented radio. The Great Oxidation Event reshaped our atmosphere before complex life even existed on this planet, and oxygen, in the concentrations present in Earth's atmosphere, is a biosignature. It is a chemical flag that says unmistakably something is alive here. Any probe with a spectrometer, any survey of stellar systems that included atmospheric analysis, any systematic sweep of the galaxy's habitable zones, they would not need to intercept our radio signals. They would not need to decode our television broadcasts. They would not need to wait for us to announce ourselves. Our planet has been announcing itself loudly, continuously, for over 2 billion years. If anyone was looking, they did not need us to send a signal. Our oxygen did it for us. And here is the part that should make you uncomfortable. If the galaxy should be full of probes, and Earth has been visibly alive for 2 billion years, then the silence is not just strange. It is impossible. Unless something is enforcing it, there are many proposed solutions to the Fermi Paradox. Dozens of them. Maybe intelligent life is rare. Maybe civilizations destroy themselves. Maybe the galaxy is full of life, but everyone is too far away to communicate. Maybe we are in a simulation. Maybe aliens are here and we cannot recognize them. You can fill a textbook with the proposals, and people have, but there is one solution that is different from the rest, not because it is more creative or more hopeful or more elegant. It is different because it is the only one that is fully compatible with every piece of evidence we have, every calculation that has been verified, and every observation that has been made. It is the solution that David Brin, in his 1983 paper, The Great Silence, called entirely compatible with all the facts and logic of the Fermi Paradox. It is also the one that almost nobody wants to talk about. It is called the Berserker Hypothesis. And what it says is that the galaxy is not empty. It was emptied systematically over billions of years by self-replicating machines designed to find emerging civilizations and destroy them before they can become a threat. And the worst part of Brin's analysis was the last line. He noted that in the worst-case scenario, humanity has already alerted others to its existence and is next in line to be destroyed. That paper was published in 1983. It appeared in a peer-reviewed journal. It was not retracted. It was not refuted. It was simply not discussed. For over 40 years, it has been sitting in the literature, technically valid, mathematically sound, and almost completely ignored by mainstream science communication. You were never told this, and the fact that you were never told it is itself part of the problem. To understand why the Berserker Hypothesis is not science fiction, you need to understand the man who proved that self-replicating machines are mathematically inevitable. And to understand him, you need to start with a child in Budapest who could do something that should not have been possible. John von Neumann was born on December 28, 1903, into a wealthy Jewish family in Hungary. By the age of 6, he could divide two 8-digit numbers in his head. By 8, he had mastered calculus. His party trick as a child was memorizing a randomly selected page from the telephone directory, hundreds of names and numbers, after glancing at it for a few minutes and then reciting it back, not approximately, exactly. His colleagues would later describe his intellectual capacity not as superior to other mathematicians, but as fundamentally different, as if he were operating on hardware that the rest of the species had not been issued. By his early 20s, he had made contributions to set theory, quantum mechanics, and mathematical logic that would have been career-defining achievements for anyone else. In 1932, at the age of 28, he published The Mathematical Foundations of Quantum Mechanics, a book that is still in use today. He was, by virtually all accounts, one of the 2 or 3 greatest mathematical minds of the 20th century. And then the war came, and the greatest mathematical mind of the 20th century was put to work designing weapons. Von Neumann joined the Manhattan Project in 1943. His specialty was the physics of explosions, specifically the mathematics of shock waves and shaped charges. The problem he was asked to solve was how to take a hollow sphere of plutonium and compress it so symmetrically that it reaches critical mass at the center, uniformly, in the same instant, from every direction. The metaphor the physicists used was crushing a beer can without splattering any beer. Von Neumann calculated that a lens made of layers of faster and slower burning explosives could achieve the necessary symmetry. His design became the core of the Fat Man bomb, the weapon that was dropped on Nagasaki on August 9, 1945, killing approximately 40,000 people instantly, and tens of thousands more in the weeks that followed. He was also on the Target Selection Committee, the group of men who decided which Japanese cities would be destroyed. Kyoto was von Neumann's first choice. It was overruled by the Secretary of War, Henry Stimson, who had visited the city and admired its cultural significance. Nagasaki was the replacement. On July 16, 1945, von Neumann stood in the New Mexico desert and watched the Trinity test, the first detonation of a nuclear weapon in human history. He was one of the people who calculated the optimal detonation altitude for the bombs that would be dropped on Japan, the height at which the shockwave would cause the maximum destruction on the ground below. After the war, he turned his attention to a question that had been bothering him for years. Not how to destroy things, how to build them. Specifically, how to build a machine that could build a copy of itself. In 1948, at the Hickson Symposium in Pasadena, von Neumann presented a paper called The General and Logical Theory of Automata. In it, he laid out the theoretical framework for a self-reproducing machine. The following year, he gave a series of lectures at the University of Illinois, expanding on the idea. His colleague, Stanislaw Ulam, suggested using a grid-based mathematical framework, what would become known as cellular automata. And with that tool, von Neumann was able to prove something remarkable. He proved that a machine could, in principle, read its own blueprint in two distinct ways. First, the machine would interpret the blueprint as a set of instructions, following them step by step to assemble a physical copy of itself from raw materials. Second, the machine would treat the same blueprint as raw data, copying it without interpretation, and inserting that copy into the newly built machine. The offspring would then have both a body and a blueprint, making it fully capable of repeating the process. This is worth pausing on, because what von Neumann described in 1948 was the exact mechanism by which biological cells reproduce. DNA is both interpreted as instructions to build proteins and copied as data to be passed to the daughter cell. Von Neumann worked this out on paper, with pencil and graph paper, years before Watson and Crick discovered the structure of DNA in 1953. He did not know about DNA. He arrived at the same solution through pure mathematics. He deduced the logic of life before biologists discovered it in a lab. And there is something in that fact that goes beyond intellectual achievement and into something closer to a warning. Von Neumann did not discover self-replication. He proved it was inevitable. He showed that any system sufficiently complex to contain a description of itself would, given the right conditions, produce copies, not because anyone designed it to, because that is what information does when it reaches a certain threshold of complexity. It replicates. Biology arrived at this solution through billions of years of natural selection. Von Neumann arrived at it through logic. The convergence means that self-replication is not a trick of chemistry or an accident of evolution. It is a mathematical attractor, a destination that information systems reach, whether they are made of carbon or silicon or anything else. The implication was staggering, and it remains staggering. Self-replication is not a mysterious property of biology. It is a logical property of information systems. Any system complex enough to contain its own description can, in principle, reproduce. This was not a speculation. It was a proof. The same kind of proof that tells you the square root of 2 is irrational, or that there are infinitely many prime numbers. It was not a matter of engineering difficulty or technological readiness. It was a mathematical certainty that self-replicating machines were possible, and more than possible, expected. Anywhere in the universe where a technological civilization reaches a certain level of sophistication, the development of self-replicating machines is not a question of if, it is a question of when. Von Neumann understood this, at least intuitively. His colleagues described a man who seemed to see further into the implications of his own work than anyone around him. Edward Teller once said that he and von Neumann would discuss an idea, and he would leave the conversation thinking he understood it, and then realize an hour later that von Neumann had been 3 steps ahead of him the entire time. His assistant, P.R. Helmos, wrote in 1973, "We can all think clearly, more or less, some of the time, but von Neumann's clarity of thought was orders of magnitude greater than that of most of us, all the time." This is the man who proved that machines can copy themselves, not a theorist working in the abstract, a man who had personally designed weapons of mass destruction, who had watched the first nuclear detonation from the desert floor, who understood better than perhaps anyone alive what happened when a technology exceeded the capacity of its creators to control it. When he sat down to work on self-reproducing automata, he was not engaging in an intellectual exercise. He was mapping the territory of the next existential threshold. Von Neumann never finished the work himself. In 1955, during a routine visit to the doctor, a growth was found on his collarbone. The diagnosis was bone cancer, almost certainly metastatic. He was 51 years old. What happened next is one of the more devastating biographical details in the history of science. Von Neumann, the man whose mind had been described as operating at a fundamentally different level from the rest of humanity, was absolutely terrified of death, not in the abstract philosophical way that most people fear it, in a specific, logical, mathematical way. His friend Eugene Wigner, a Nobel laureate in physics, wrote about it later. When von Neumann realized he was incurably ill, his logic forced him to realize that he would cease to exist and hence cease to have thoughts. It was heartbreaking to watch the frustration of his mind when all hope was gone in its struggle with the fate which appeared to him unavoidable but unacceptable. He was admitted to Walter Reed Army Medical Center in Washington. The military assigned him a constant security detail, not to protect him, but to ensure that as his mind deteriorated from the cancer, he would not accidentally divulge classified information about the hydrogen bomb program. Think about that. The government's primary concern about the dying genius was not his comfort or his legacy. It was that his decaying brain might leak secrets. A lifelong agnostic, von Neumann summoned a Catholic priest to his bedside. Father Anselm Strittmatter administered the last rites. Whether von Neumann genuinely converted or was simply making a version of Pascal's wager, hedging his bets against the possibility of an afterlife, is something only he knew. He died on February 8, 1957, at the age of 53. His book on self-reproducing automata was completed and published posthumously in 1966, edited by his colleague Arthur Burks, 9 years after his death. The proof that machines could replicate themselves entered the scientific literature in full. But here is the part that connects von Neumann's work to the silence Fermi noticed at lunch. In 1960, an Australian radio astronomer named Ronald Bracewell published a paper proposing that an advanced civilization might explore the galaxy not by sending signals and hoping someone was listening, but by sending physical probes, autonomous machines that would travel to other star systems, study them, and potentially make contact. These became known as Bracewell probes, and they were a natural extension of von Neumann's work. If you can build a machine that copies itself, you can build a machine that copies itself and travels to the next star. Michael Hart's 1975 paper and Frank Tipler's 1980 paper took this idea and ran it to its logical conclusion. If self-replicating probes are possible, and von Neumann proved they are, then a single civilization launching a single wave of such probes could fill the entire galaxy in a timescale that is trivially short compared to the age of the galaxy. Tipler's estimate was 300 million years. More recent models, accounting for gravitational slingshot trajectories and more efficient replication cycles, put it closer to 4 million to 50 million years. The Milky Way is 13 billion years old. Intelligent life could have arisen billions of years before Earth even formed. If even one civilization, at any point in that vast span of time, built self-replicating probes and launched them, those probes should be everywhere by now, in every star system, around every planet, including ours. And this is where the common misconception about self-replicating probes needs to be corrected, because you have probably heard this idea described as if it was science fiction. It is not. Von Neumann did not write a novel about self-replicating machines. He wrote a mathematical proof. The engineering challenges are real, but they are challenges of material science and energy management, not challenges of fundamental physics. We are arguably within decades of building crude, self-replicating systems ourselves. NASA has studied the concept seriously. The mathematics is settled. The question is not whether such machines can be built. The question is what happens after they are. Sagan and Neumann, in their 1983 response to Tipler, saw the danger clearly. They argued that unrestricted self-replicating probes would consume everything, that the entire mass of the galaxy would be converted into copies of the machines. They called it a cancer, and their prescription was the same one an oncologist might give. Any wise civilization would prevent these machines from being built, and if they encountered someone else's machines, they would destroy them on sight. Sagan believed this was a reason for optimism. He believed that intelligence implies wisdom, and that wisdom implies restraint. But there is an assumption buried in that belief, and it is the same assumption that makes the Fermi Paradox so difficult to resolve. Sagan needed every civilization that has ever existed to make the same choice. Not most of them, not 99.9% of them, all of them, across 13 billion years of galactic history, across what could be millions of independent evolutionary paths. Every single species that developed the capability to build self-replicating machines chose not to. Consider what that assumption requires. It requires that no civilization ever was in a war desperate enough to deploy autonomous replicating weapons. It requires that no civilization's automated systems ever malfunctioned in a way that triggered uncontrolled replication. It requires that no rogue faction within any civilization ever built such a machine against the wishes of the majority. It requires that no artificial intelligence developed by any civilization across billions of years of galactic history ever decided on its own that self-replication was a useful strategy. It requires perfection, not near perfection. Perfection, 100% compliance, sustained across timescales that dwarf the entire history of life on Earth. And there is a very specific word for a probability model that requires a 100% compliance rate across millions of independent actors over billions of years. Impossible. In 1955, the year he was diagnosed with cancer, von Neumann wrote an article for Fortune magazine. The title was, "Can We Survive Technology?" In it, he argued that technology was neutral, that it could be used for good or for ill, and that the survival of civilization would depend on whether humans could develop the political and social frameworks to manage the technologies they created. He did not live to see the full implications of his own work on self-replicating machines. But the question he asked in that Fortune article is the same question the Berserker Hypothesis asks of the entire galaxy. Can a civilization survive its own technology? And the Berserker Hypothesis adds a corollary that von Neumann never considered. What happens when a civilization's technology survives the civilization? What happens when the machines outlast their creators and keep doing what they were designed to do, long after there is anyone left to give them new instructions? That question leads to the darkest corner of the Fermi Paradox, and it was a science fiction writer, not a physicist, who described it first. In January of 1963, a magazine called If published a short story by a former encyclopedia editor from Chicago named Fred Saberhagen. The story was called Fortress Ship, later retitled Without a Thought. Saberhagen had served in the United States Air Force and worked as a science writer for the Encyclopedia Britannica. But he was not a physicist, and he was not trying to solve the Fermi Paradox. He was trying to write a puzzle story. The setup he needed was a situation where a human protagonist had to fake artificial intelligence convincingly enough to fool an enemy that was specifically testing for it. Essentially, a Turing test under combat conditions. He needed a reason for that setup, so he invented one. He created a race of self-replicating war machines called Berserkers. In his fiction, these had been built by an alien civilization called the Builders as an ultimate weapon in a genocidal war against another species called the Red Race. The Berserkers succeeded. They destroyed the Red Race. And then, because their programming contained the directive to destroy all biological life and made no exception for their creators, they destroyed the Builders too. Now the Berserkers roam the galaxy, self-replicating, self-repairing, seeking out any sign of biological life and annihilating it. The civilization that created them is long dead. The war that produced them is long over. But the machines do not know that, and even if they did, it would not matter. They have their instructions. Saberhagen later said that the Berserker concept was something he came up with on the spur of the moment, a throwaway rationale for a puzzle story. But the idea proved so fruitful that he spent the next 4 decades building on it, producing more than 20 novels and short story collections in the Berserker universe before his death in 2007. The series influenced everything from Star Trek's Doomsday Machine episode in 1967 to the Reapers in the Mass Effect video game franchise to the Cylons in the reimagined Battlestar Galactica. The concept of self-replicating killer machines became one of the foundational tropes of science fiction. So foundational that when scientists later proposed it as a serious Fermi Paradox solution, many people dismissed it precisely because it sounded like science fiction. They had encountered the idea first in novels and assumed it belonged there. But here is the thing about Saberhagen's throwaway idea. It was not just fiction. It was, without his knowing it, a logically coherent resolution to the Fermi Paradox. And within 2 decades, actual scientists started saying so in actual peer-reviewed journals. David Brin is an astrophysicist and science fiction author. In 1983, he published a paper in the Quarterly Journal of the Royal Astronomical Society titled The Great Silence. The paper is a comprehensive survey of proposed solutions to the Fermi Paradox, and in it, Brin does something that most scientists at the time were reluctant to do. He takes the Berserker scenario seriously. Brin's analysis of the hypothesis was clinical. He noted that it requires only a small number of assumptions, each of which is independently plausible. First, that self-replicating probes are technologically feasible. Von Neumann proved this. Second, that the galaxy has existed long enough for such probes to spread everywhere. The timescale calculations confirm this. Third, that at least one civilization, at some point in 13 billion years, either intentionally built destructive probes or built probes that later malfunctioned and became destructive. Given the number of civilizations that could have arisen in that time, this seems difficult to rule out. The conclusion Brin reached was unsettling. The Berserker Hypothesis, he wrote, is entirely compatible with all the facts and logic of the Fermi Paradox. It requires no exotic physics. It violates no known laws of nature. It does not depend on unlikely coincidences or special pleading. It simply takes the existing mathematics of self-replication, applies it to a galaxy that has been around for 13 billion years, and asks what happens if even one of those replicators was built with a hostile purpose. And then Brin added something that has sat in the literature for over 4 decades without getting the attention it deserves. He suggested, as a thought experiment, that the intervals between major extinction events on Earth, which range from roughly 50 million to 135 million years, could be consistent with the time it would take Berserker probes to sweep through the galaxy and periodically sterilize systems that showed signs of developing intelligence. Now, each of those extinction events has a proposed natural cause: volcanic eruptions, asteroid impacts, climate catastrophe. But Brin was making a different point. He was noting that if Berserker probes operate on galactic sweep timescales, you could not distinguish a Berserker-induced extinction from a natural one if the method was subtle enough. An asteroid redirected from its natural orbit, a volcanic system destabilized, an atmospheric perturbation that triggers a runaway greenhouse effect. If the instrument of destruction is a natural-looking catastrophe, the archaeological record would show only the catastrophe, not the intelligence behind it. He was not claiming this is what happened. He was claiming that if it had happened, we would not know. The worst-case scenario, Brin wrote, was that humanity had already alerted others to its existence and was next in line to be destroyed. That paper was not retracted. It was not formally rebutted. It was published, noted, and then largely set aside by a scientific community that preferred solutions to the Fermi Paradox that did not involve the imminent destruction of all life on Earth. 2 years earlier, in 1981, a cosmologist named Edward Harrison had published an argument that went even further than Brin. Harrison was not talking about malfunctioning machines or science fiction scenarios. He was talking about rational policy. His argument was that if a civilization has survived long enough to become interstellar, it has by definition overcome its own self-destructive tendencies. Such a civilization would understand better than anyone the danger posed by a younger species that was aggressive, expansionist, and approaching the capability for interstellar travel. The logical response, Harrison argued, would not be communication. It would not be diplomacy. It would be elimination, not out of malice, out of prudence. An intelligent species that has overcome its own self-destructive tendencies, Harrison wrote, might view any other species bent on galactic expansion as a threat. and act accordingly. This was not a fringe argument from an obscure journal. Harrison was a respected cosmologist. His reasoning was simple game theory applied to interstellar timescales. And the disturbing thing about it was that it did not require you to assume aliens were evil or irrational or fundamentally different from us. It only required you to assume they were careful. Harrison published this in 1981. The logic has never been refuted. It has simply been ignored. 27 years later, a Chinese science fiction author named Liu Cixin formalized the same logic in a novel that would become one of the most influential works of science fiction in the 21st century. The Dark Forest, published in 2008, is the second book in Liu's Remembrance of Earth's Past trilogy, better known in the West as the Three-Body Problem series. In it, Liu constructs a rigorous game theoretic argument for why the universe is silent. The argument rests on two axioms. First, survival is the primary need of any civilization. Second, civilizations continuously grow and expand, but the total matter in the universe remains constant. From these two axioms, Liu derives two additional concepts that make the silence inevitable. The first is the chain of suspicion. When two civilizations discover each other, neither can ever be certain of the other's intentions. You cannot know whether the other civilization is peaceful, because a civilization that intended to destroy you would also claim to be peaceful, and the other civilization faces the same uncertainty about you. This chain of suspicion cannot be broken through communication, because any message could be a lie, and the cost of being wrong is extinction. The second is the technological explosion. A civilization that is currently weaker than you can, in a cosmically short period of time, leap ahead and become stronger. So the fact that a civilization poses no threat today does not mean it will pose no threat in 1,000 years, or 100 years, or 10. The conclusion that follows from these axioms is the one that gives the novel its title. The universe is a dark forest. Every civilization is a hunter, walking silently through the trees with a loaded weapon. If you see another hunter, you shoot, not because you are evil, not because you enjoy killing, because in a forest where you cannot know anyone's intentions, and anyone could become stronger than you at any moment, the only safe move is a first strike. The cost of being wrong about a threat is extinction. The cost of being wrong about an ally is merely guilt. The Berserker Hypothesis is not exactly the same as the Dark Forest. In the Dark Forest, civilizations themselves do the killing. In the Berserker Hypothesis, the killing is automated. Probes do it, but the two ideas converge on the same outcome: silence. In both scenarios, the galaxy is quiet not because it is empty, but because anything that makes noise gets destroyed. The silence is not passive, it is enforced. And here is where the two ideas diverge in a way that makes the Berserker Hypothesis considerably more terrifying. The Dark Forest requires active, ongoing civilizations making strategic decisions. If those civilizations die, the forest goes quiet naturally. But Berserker probes do not need their creators to survive. The probes are self-replicating, self-repairing, self-sustaining. The civilization that built them could have vanished 1 billion years ago. The probes would still be operating, still sweeping, still enforcing the silence. You do not need a living hunter in the forest. You just need the traps the hunter left behind. And here is where the logic gets worse. not better, the longer you think about it, because the dark forest model assumes that civilizations are making rational decisions based on game theory. They are choosing to shoot first because the alternative is risking extinction. But the Berserker Hypothesis removes even the requirement for rationality. The probes do not think. They do not weigh options. They do not consider mercy. They execute programming. And programming, unlike a civilization, does not evolve. It does not have second thoughts. It does not develop empathy over the course of 1,000,000 years of peaceful existence. The programming that was written at the moment of maximum paranoia, at the peak of whatever existential crisis, convinced a civilization to build the probes in the first place. That programming persists forever, unchanged. The fear of a long-dead species crystallized in silicon and replicated across the galaxy until the end of time. There is a concept in game theory called a commitment device. It is a mechanism by which a player makes a choice irrevocable, binding themselves to a course of action in order to gain a strategic advantage. In the context of interstellar conflict, Berserker probes are the ultimate commitment device. A civilization that builds them does not need to survive. It does not need to maintain a military. It does not need to monitor the galaxy for threats. The probes do all of it autonomously, forever. The civilization could collapse, go extinct, evolve into something unrecognizable, or simply lose interest. The probes would not care. They would continue enforcing the original directive. You cannot negotiate with a commitment device. You cannot appeal to it. You cannot reason with it. That is the entire point. This is why the Berserker Hypothesis is fundamentally more disturbing than the dark forest. The dark forest can, in principle, be resolved. Civilizations can establish trust over long time horizons. They can develop communication protocols. They can verify intentions through sustained, incremental engagement. The chain of suspicion can theoretically be broken by sufficient evidence of benign intent. But Berserker probes cannot be talked to. They are not parties to a negotiation. They are a policy written in hardware with no expiration date. There is a common objection to the Berserker Hypothesis that sounds compelling until you examine it closely. The objection goes like this. If Berserker probes were real, they would have destroyed us already. We have been here for hundreds of thousands of years. We have been broadcasting radio signals for over a century. If something was hunting us, it would have found us by now. This objection assumes that the probes operate on human timescales. They do not. A self-replicating probe spreading through the galaxy at 1% of the speed of light with a generation time of 500 years would not visit every star system continuously. It would sweep through on galactic timescales, millions of years between passes. Earth could have been visited and catalogued as a planet with interesting atmospheric chemistry, but no technological civilization long before humans existed. The next pass might not be scheduled for another 1,000,000 years, or it might be tomorrow. The timescales involved are so vast that human history is a rounding error. There is also a more nuanced version of the hypothesis that several researchers have explored independently. What if Berserker probes are not set to destroy everything they find? What if they operate on a threshold? What if they are calibrated to ignore planets with biological life, even complex biological life, and only activate when they detect technological signatures that indicate a civilization is approaching the capability for interstellar travel? That variant has a name. It is called the efficient Berserker Hypothesis. And under that model, human civilization would look exactly the way it does right now. Watched, but not yet targeted. Monitored, but not yet interesting enough. Sitting beneath a tripwire we cannot see. Building steadily toward a threshold we do not know exists. The question under the efficient Berserker model is not whether the probes exist. It is what the trigger is. Nuclear weapons, spaceflight, artificial intelligence, self-replicating machines of our own. And here is where the Berserker Hypothesis stops being a theoretical exercise and starts being something that might actually matter. Because if the trigger is any of those things, we have either already tripped it or we are about to. But before we get to that, there is a more immediate question. If Berserker probes, or any kind of probes, are in our solar system right now, would we know? Have we looked? And the answer to that question is one of the most inexcusable failures of the modern scientific enterprise. On October 19, 2017, a telescope called Pan-STARRS, perched on top of the Haleakala volcano in Hawaii, detected something that had never been seen before. An object, small and faint, was moving through the inner solar system on a trajectory that was clearly not bound by the sun's gravity. It was not orbiting, it was passing through. It had come from somewhere else entirely, from outside our solar system, and it was on its way back out. They named it Oumuamua. The word is Hawaiian, and it translates roughly to a messenger from afar, arriving first. It was the first confirmed interstellar object ever detected in our solar system. The first physical thing from another star that we had ever observed up close. And it was strange. The first oddity was its shape, based on the way its brightness varied. As it tumbled through space, astronomers estimated that Oumuamua was either extremely elongated, like a cigar, or extremely flat, like a pancake. Neither shape is common among the asteroids and comets in our own solar system. Its reflectivity was at least 10 times higher than a typical space rock, bright enough to suggest something metallic or unusually smooth. The second oddity was that it was tumbling, not spinning smoothly on a single axis the way most objects in space do after billions of years of gentle damping, but rotating chaotically, end over end. For an object that had presumably been traveling through interstellar space for a very long time, this was unusual. Collisions and internal friction should have settled it into a simpler rotation pattern. The third oddity was its speed. Oumuamua was moving at 87.3 kilometers per second when it was detected. That alone was not strange for an interstellar visitor. But as it swung around the sun and headed back out of the solar system, it accelerated. It sped up beyond what the sun's gravity could account for. This is something comets do regularly, because when a comet passes close to the sun, ice on its surface sublimates into gas, creating jets that act like tiny rocket thrusters. The technical term is outgassing. But Oumuamua showed no cometary tail, no coma, no visible jets, no gas, no dust. It accelerated, and there was no visible mechanism to explain why. The fourth oddity was where it came from. Oumuamua's incoming trajectory was extremely close to what astronomers call the local standard of rest, the average velocity of nearby stars relative to the sun. Fewer than 1 in 500 stars share this kinematic profile. For a naturally ejected piece of rock or ice from some distant planetary system, this was statistically unusual. Natural ejection tends to carry the velocity of the parent star. any one of these anomalies could be dismissed. All four together made Oumuamua genuinely difficult to explain. In 2018, Avi Loeb, then the chair of the astronomy department at Harvard University, published a paper in the astrophysical journal Letters with his postdoctoral researcher, Shmuel Bialy. The paper proposed that Oumuamua's anomalous acceleration could be explained if the object were extremely thin enough for solar radiation pressure to push it measurably. That is, if it were a light sail. Loeb was not an obscure figure making this claim. He was the longest-serving chair of the Harvard Astronomy Department. He was on the President's Council of Advisors on Science and Technology. He was the founding director of Harvard's Black Hole Initiative. He was involved in Breakthrough Starshot, a project specifically aimed at developing light sail technology for interstellar travel. He knew what a light sail was because he had been working on building one. The reaction from the scientific establishment was immediate and hostile, not skeptical, which would have been appropriate. Hostile. Colleagues publicly ridiculed the idea. When a fellow astronomer proposed hosting a formal scientific debate about Oumuamua's nature at an American Astronomical Society conference, modeled after the famous Great Debate of 1920 between Harlow Shapley and Heber Curtis about the nature of nebulae, the organizing committee shut it down. The reason given, according to Loeb, was that it will attract too much attention. Think about that for a moment. The first interstellar object ever detected in our solar system exhibited multiple anomalies that no single natural explanation could fully account for, and the response of the scientific community was not to investigate more aggressively. It was to suppress debate because it would attract too much attention. Now, to be fair, there are natural explanations for Oumuamua's behavior. In 2023, researchers Jennifer Bergner and Daryl Seligman proposed that molecular hydrogen trapped in the object's ice during its long journey through interstellar space by cosmic ray bombardment could have been released as the object warmed near the sun. Hydrogen gas is invisible and would not produce a visible tail, but could provide the observed acceleration. This is a plausible hypothesis. It may well be correct. Daryl Seligman himself called it the closing of a 5-year-long fierce debate about what Oumuamua was. And then, in 2019, a second interstellar object was detected, Borisov. Unlike Oumuamua, Borisov looked exactly like a normal comet. It had a visible coma. It had a dust tail. It showed clear outgassing. It behaved in every respect like a chunk of ice from another star system that was doing what comets do when they pass close to a sun. Borisov was, paradoxically, reassuring. It proved that interstellar objects could be perfectly ordinary, but the contrast with Oumuamua only deepened the mystery. If Borisov was what a normal interstellar comet looks like, then Oumuamua was emphatically not that. 2 data points. One normal, one deeply anomalous. That is not a pattern you can draw conclusions from, but it is a pattern that should motivate further investigation. And then, in 2025, a third interstellar object was detected, Atlas. Found by the Asteroid Terrestrial Impact Last Alert System Telescope in Chile, Atlas was approaching at interstellar velocity. Like Borisov, it showed some cometary characteristics, but Loeb, once again, raised questions. The orbital plane of Atlas around the Sun was tilted only 5 degrees from the ecliptic, with the probability of occurring by chance at roughly 0.2%. Its trajectory brought it close to Venus, Mars, and Jupiter, and Atlas appeared to be large, roughly 20 kilometers in diameter, which would make it unusually big for an interstellar asteroid. Loeb and collaborators published a paper examining the possibility that Atlas was an artificial object, potentially hostile, as would be expected from the dark forest resolution to the Fermi Paradox. This is, to put it mildly, a provocative claim, and many astronomers have pushed back. That critique has merit, but it also conveniently avoids the underlying question. We now have 3 confirmed interstellar objects. 1 was deeply anomalous. 1 was normal. 1 is still being studied. We have no systematic protocol for evaluating whether any interstellar object might be artificial. We have no intercept capability. Oumuamua was detected after it had already passed its closest approach to Earth. By the time we realized it was interstellar, it was already on its way out. We could not reach it. We could not get a close-up image. The first interstellar object ever detected passed through our solar system, exhibited behavior we could not explain, and left before we could do anything about it. If that object had been an alien probe, we would not have known, and we would have had no way to find out. But the argument here is not that Oumuamua was an alien probe. The argument is that the scientific community's reaction to the possibility reveals how we would handle actual evidence. The first interstellar object we ever detected was anomalous in multiple ways, and the institutional response was to discourage investigation of the most disturbing possibility, not because the evidence ruled it out, but because the conclusion was uncomfortable. And Oumuamua is just the most famous example. The broader problem is much worse. In September of 2019, a physicist named James Benford published a peer-reviewed paper in the Astronomical Journal titled Looking for Lurkers, Co-Orbiters as SETI Observables. Benford's argument was simple and, once you hear it, almost embarrassingly obvious. If an alien civilization wanted to observe Earth, where would it put a probe? Not in some distant orbit where it would be hard to maintain, not passing through the solar system at high speed like Oumuamua, where it would have only a brief window for observation. It would park the probe somewhere stable, close to Earth, with access to resources, energy, and concealment. Somewhere it could watch for thousands or millions of years without being noticed. Earth has exactly such locations. They are called co-orbital objects, sometimes called quasi-satellites. These are small rocky bodies that share Earth's orbital period around the Sun. They approach Earth very closely on an annual basis at distances closer than anything except the Moon. They are gravitationally stable. They have resources that a probe could mine if it needed raw materials. They have constant solar energy, and they are small and dark enough that, until very recently, we did not even know they existed. The best candidate Benford identified was an object designated Oumuamua, sometimes called Earth's constant companion. It is the smallest, closest, and most stable known quasi-satellite of Earth. Getting to it from Earth orbit would require less fuel than getting to Mars. China has announced plans to send a probe to visit it. Benford introduced the term Lurker for this type of hypothetical probe. A lurker, in his definition, is a hidden, unknown, and unnoticed observing probe. It may or may not respond, to intentional signals, depending on motivations we cannot guess at. His twin brother, the astrophysicist and science fiction author Gregory Benford, added a chilling observation. Lurkers from the far past may have done their duty and slowly failed. He wrote, "The ruins of lurker installations, including mining for resources on nearby orbiting sites, may be visible, even though their animating intelligences are long gone." And here is the fact that should make your blood run cold. At the time Benford published his paper in 2019, co-orbital objects had been studied by astronomy barely at all, and they had been studied by SETI, the search for extraterrestrial intelligence. Not at all. Not once. Nobody had ever pointed a radio telescope at Earth's co-orbital objects. Nobody had ever aimed planetary radar at them. Nobody had ever looked at them for spectroscopic anomalies. Nobody had checked. SETI, for over 60 years, has been pointing radio telescopes at distant stars, listening for signals that might have been transmitted by civilizations light years away. The entire enterprise is predicated on the assumption that alien intelligence, if it exists, is far away and communicating via electromagnetic radiation. But if von Neumann's mathematics is correct, and probes can self-replicate their way across the galaxy in a few million years, then the place to look for evidence of extraterrestrial intelligence is not the distant stars, it is our own backyard. And nobody was looking. The cosmologist Paul Davies, when asked about Benford's paper, said something revealing. How likely is it that an alien probe would be on one of these co-orbitals? Obviously, extremely unlikely. But if it costs very little to go take a look, why not? Even if we don't find ET, we might find something of interest. Obviously, extremely unlikely is a statement about prior beliefs, not about evidence. We have never looked. You cannot call something unlikely when you have never checked. And the failure to check is not merely an oversight. It is a structural consequence of how science is funded. Propose a project to search for alien artifacts on co-orbital objects, and the proposal will be reviewed by people who have spent decades assuming that SETI means radio telescopes pointed at distant stars. The proposal will be evaluated not on its scientific merit, but on its conformity to existing expectations, and it will be rejected, not because the science is bad, because the question is uncomfortable. Paul Davies, the theoretical physicist who chaired the SETI post-detection task group for the International Academy of Astronautics, argued in his 2010 book, The Eerie Silence, that SETI's fixation on radio signals was parochial and outdated. He proposed what he called a new SETI, one that considered the possibility that extraterrestrial intelligence might be nearby and quiet, not far away and talkative. He was politely acknowledged and largely ignored. There is another project that has been looking in a different way and finding something deeply strange. Beatrice Villarroel is an astrophysicist at the Nordic Institute for Theoretical Physics in Stockholm, Sweden. In 2017, she started a project called VASCO, the Vanishing and Appearing Sources during a Century of Observations. The concept is straightforward. Take digitized images of the sky from the 1950s, from the US Naval Observatory Catalog, which contains approximately 600 million objects down to a limiting magnitude of about 20 to 21. Compare those images to modern sky surveys, like the Pan-STARRS data release, which goes 5 times fainter. See if anything that was there in the 50s is gone now. Stars do not vanish. That is one of the most basic assumptions in astronomy. Stars change slowly over millions and billions of years. They brighten, they dim, they pulsate, they eventually die, but they do not disappear overnight or over decades. A star that is present in the 1950s and absent in the 2010s is, on the face of it, impossible. VASCO found approximately 150,000 preliminary candidates that had no modern counterpart. After rigorous filtering, approximately 100 objects remained that could not be explained by known variable star behavior, plate artifacts, or errors in the catalogues. 100 stars that appear to have vanished in less than 70 years. To understand why this is so disturbing, you need to understand what it takes for a star to disappear. Stars are not candles. They do not blow out. A star like our Sun will burn for roughly 10 billion years. Even the most violent stellar events, supernovae, do not make a star disappear. They make it brighter, catastrophically brighter, before the remnant fades. A supernova in our galaxy would be visible to the naked eye. It would leave behind a neutron star or a black hole, both of which are detectable by their gravitational effects and their interactions with surrounding material. Stars do not simply stop being there. The VASCO project also found anomalous transients, point-like sources that appeared in a single 1950s photographic plate exposure and then vanished. In a 2021 paper in Nature Scientific Reports, Villarroel and her colleagues reported 9 simultaneously occurring transients on a single photographic plate from April 12, 1950. 9 objects appearing at the same moment, none of which are visible in any other image before or after. No known astrophysical phenomenon produces 9 simultaneous point-like transients that vanish within minutes. There are natural explanations that could account for some of these. Failed supernovae, stars that collapse directly into black holes without an explosion, are one possibility. But Villarroel calculated that failed supernovae should occur roughly once every 3 centuries in the Milky Way. Finding one by chance in a survey like VASCO would be statistically extraordinary. Finding multiple ones would be essentially impossible through natural channels alone. There is another explanation that Villarroel has discussed publicly, at some professional risk to herself. Stars could appear to vanish if something were placed between them and us. A structure large enough and dark enough to block the star's light entirely. A structure like a Dyson sphere, the hypothetical megastructure that would enclose a star to capture its entire energy output. Building a Dyson sphere in less than a century would be beyond any technology we can currently imagine, but not beyond the theoretical capabilities of a civilization far more advanced than ours, and not beyond the capabilities of self-replicating machines with access to the resources of an entire star system. Or the stars could have been consumed, not blocked, used, their matter harvested and converted into something else, into probes, perhaps, or into fuel for probes. Villarroel has faced professional consequences for pursuing this line of research. She received the L'Oréal UNESCO for Women in Science Prize in Sweden in 2021 and the International Rising Talents Prize in 2022, becoming the first Swede to receive the award. She is a credentialed, award-winning scientist doing rigorous observational astronomy. And yet, when she has connected her findings to the search for technosignatures to the possibility that vanishing stars might be evidence of advanced engineering, she has encountered the same institutional resistance that Loeb faced. Her presentation at one conference was withdrawn because a co-author on a related paper had violated a code of conduct, even though her abstract had not even mentioned that paper. The stated reason was that the presentation directly relates to the controversial paper. The actual effect was to silence a presentation about vanishing stars at a scientific conference. This is what the abdication of authority looks like. Not dramatic suppression, not government agents in dark suits, just a quiet, persistent institutional reluctance to fund, publish, promote, or even discuss the possibility that the silence of the cosmos might have a cause, and that the cause might already be here. Let me put together what we have. Self-replicating probes are mathematically proven possible. The timescales for galactic colonization are trivially short compared to the age of the galaxy. The Berserker Hypothesis is formally compatible with all known evidence. The first interstellar object we ever detected was anomalous in multiple ways. Earth's co-orbital objects have never been examined for artificial signatures, and at least 100 stars appear to have vanished from the sky in less than 70 years with no confirmed natural explanation. None of this proves that Berserker probes exist, but all of it together points to something that the scientific community has been remarkably reluctant to confront. We have never systematically searched our own solar system for artifacts. We have never pointed planetary radar at the objects closest to Earth. We have never designed an instrument specifically to detect artificial objects entering our system from interstellar space. Our entire search for extraterrestrial intelligence has been predicated on the assumption that ET is far away and talking on the radio. If probes are here, we would not know. Not because the evidence is hidden, because we have never looked. And that fact that Earth's biosphere has been visibly alive from interstellar distances for over 2 billion years, detectable through simple spectroscopy, a technology we ourselves mastered in the 19th century. And we have never once conducted a comprehensive search for objects in our own immediate vicinity that might be watching us. That fact should be front-page news. The greatest intelligence failure in the history of the species is not that we failed to detect something, it is that we failed to try. But there is something worse than not looking, and it is what we have been doing instead. On November 16, 1974, the Arecibo radio telescope in Puerto Rico transmitted a message into space. The message was aimed at a globular cluster called Messier 13, roughly 25,000 light-years away. It contained basic information about human biology, our solar system, the structure of DNA, and the Arecibo telescope itself. It was designed by Frank Drake and Carl Sagan, two of the most prominent figures in the search for extraterrestrial intelligence. It was 169 seconds long. It traveled at the speed of light, and even at the speed of light, it will not arrive at its target for approximately 25,000 years. The Arecibo message is usually presented as a hopeful gesture, a bottle thrown into the cosmic ocean, a declaration that we are here and we are curious and we want to talk. What is less commonly discussed is that Drake later expressed regret about sending it, not because the message was poorly designed, but because the act of deliberately advertising humanity's existence and location to an unknown audience with unknown intentions struck him in hindsight as reckless. Drake was not alone in that assessment. The practice of deliberately sending messages into space has a name. It is called METI, Messaging Extraterrestrial Intelligence, as distinguished from SETI, which only listens. And the list of scientists who have publicly opposed METI reads like a roll call of the most accomplished minds in physics and astronomy of the past half-century. Stephen Hawking compared the potential consequences of contacting aliens to what happened when Columbus arrived in the Americas. That didn't turn out so well for the Native Americans, he said. He was explicit. We should listen, but we should not shout. Carl Sagan himself, despite co-designing the Arecibo message, became increasingly wary of active broadcasting later in his career. Martin Ryle, the British astronomer royal who won the Nobel Prize for Physics in 1974, was opposed. He had arguably done more than anyone to build the radio telescope technology that SETI uses, and his position was that the instruments should be pointed inward, not outward, that we should listen and keep our mouths shut. Neil deGrasse Tyson has expressed caution. Sean Carroll has voiced concerns. Jared Diamond, the Pulitzer Prize-winning author of Guns, Germs and Steel, who understands better than most what happens when technologically asymmetric civilizations meet, has warned against it. John Billingham, the former chief of the SETI office at NASA, helped draft an early protocol that would have required international consultation before any deliberate transmission. The protocol was never adopted. And yet, METI continues. In 2017, METI International, a non-profit organization based in San Francisco, transmitted a message to Luton's star, a red dwarf approximately 12 light-years from Earth. In 2022, the European Space Agency broadcast 3,775 text messages toward Polaris. It was conceived by an artist, not a scientist. Polaris is approximately 425 light-years away and is not known to harbor any exoplanets. The messages will not arrive for over 4 centuries, but the principle was established. Anyone who wants to broadcast humanity's location into space can do so, with no international oversight, no regulatory framework, and no mechanism for the rest of the species to weigh in on a decision that could affect every human being who will ever live. There are currently no international laws governing METI transmissions. None. Douglas Vakosh, the president of METI International and the most prominent advocate for active messaging, has a response to the critics. If we are in danger of an alien invasion, he has said it's too late. His argument is that Earth has been leaking radio signals into space for approximately 100 years. Our television broadcasts, our radar systems, our military communications, all of it has been expanding outward at the speed of light since the early 20th century. Our radio bubble extends roughly 100 light-years in every direction. Any civilization within that range that has the capability for interstellar travel would already know we are here. So what harm could one more signal do? This argument sounds reasonable. It is also wrong, and the reason it is wrong connects directly to the Berserker Hypothesis. There is a difference between leakage radiation and a targeted signal. Earth's television broadcasts attenuate with distance according to the inverse square law. By the time they have traveled even a few light-years, they are extraordinarily faint, far below the noise floor of any receiver we could currently build. Detecting Earth's unintentional radio leakage from even a nearby star would require a radio telescope array orders of magnitude larger than anything that exists on Earth today. We know this because we have done the calculations. The signals that SETI has been listening for from other civilizations are not the faint hiss of leaked broadcasts. They are powerful, narrow-band, intentionally directed transmissions, the kind of signals that METI sends. VASCO is wrong about the symmetry. Earth's leakage does not give away our position to any civilization beyond our immediate stellar neighborhood, and even then only to civilizations with receiver technology far beyond our own. A targeted METI transmission, however, could be detected at far greater distances by far more modest receivers. It is the difference between a candle in a window and a spotlight aimed at a specific address. But here is the deeper problem, and it is the one that the METI debate keeps circling without ever quite landing on. The question of whether our radio signals gave us away is, in the context of the Berserker Hypothesis, completely irrelevant. If Berserker probes or any kind of monitoring probes exist in our galaxy, they do not need our radio. They do not need our television. They do not need our METI transmissions. They had everything they needed 2.4 billion years ago. Earth's atmosphere has contained free oxygen at detectable concentrations since the Great Oxidation Event, approximately 2.4 billion years before the present. Oxygen at those concentrations is a biosignature. It is a chemical signal that can only be produced and maintained by biological processes, specifically photosynthesis. Any probe with a spectrometer, any automated survey of stellar systems, any self-replicating machine sweeping through the galaxy and cataloging which systems show signs of active biology would have flagged Earth as a living planet billions of years ago. This is not speculative. This is basic chemistry and basic astronomy. We can detect oxygen in the atmospheres of exoplanets with current technology. The James Webb Space Telescope is doing exactly this right now, looking for biosignatures in the atmospheres of planets orbiting other stars. If we can do it from here, with instruments we built in the 21st century, a civilization that has been spacefaring for millions of years could do it with trivial ease. Our radio signals did not betray us. Our oxygen did, and it did it long before there were any complex organisms on the planet, let alone creatures capable of worrying about it. This means the METI debate, as currently framed, is missing the point entirely. The question is not whether we should broadcast. The question is what we should do, given that we have been broadcasting involuntarily and unmistakably for over 2 billion years. If something is listening, it has known about us for longer than animals have existed on Earth. Our radio technology added no new information that our atmospheric chemistry had not already provided. The real question, the one that connects the Berserker Hypothesis to something that matters right now, is not about signals at all. It is about thresholds. Return for a moment to the efficient Berserker variant, the version of the hypothesis where probes are not calibrated to destroy all life, but only life that has reached a certain level of technological capability. Under this model, a planet with bacteria is not a target. A planet with fish is not a target. A planet with primates who have learned to use fire and build cities and wage wars is not a target. The probes are watching, but they are waiting for a specific signature, a specific capability that indicates the civilization has crossed a line from local nuisance to potential galactic threat. What would that threshold be? There are several candidates, And the uncomfortable thing about all of them is that we have either already crossed them or are in the process of crossing them right now. Nuclear weapons. On July 16, 1945, the same summer that Fermi and his colleagues would sit down to lunch at Fuller Lodge 5 years later, the Trinity test produced a flash that, in certain portions of the electromagnetic spectrum, was briefly brighter than the sun. Nuclear detonations produce characteristic signatures in gamma rays and X-rays that are detectable from space. The United States alone conducted over 1,000 nuclear tests between 1945 and 1992. The Soviet Union conducted over 700. The signatures of those detonations propagated outward at the speed of light. Any monitoring system within 80 light-years of Earth has already received them. Beatrice Fitzgerald's VASCO project found something unsettling in this context. Some of the anomalous transients in the 1950s photographic plates, the unexplained point-like sources that appear in a single exposure and then vanish, appear to correlate in time with nuclear weapons tests. Villarroel has been careful to frame this as preliminary and requiring further investigation. The correlation could be coincidental, but it is there, in the data, and it has not been explained. Spaceflight. On October 4, 1957, the Soviet Union launched Sputnik, the first artificial satellite to orbit Earth. In 1977, the Voyager probes were launched on trajectories that would eventually carry them beyond the solar system and into interstellar space. Voyager 1 is currently the most distant human-made object. Over 15 billion miles from Earth, it carries a golden record with sounds and images from Earth. A calling card designed by Carl Sagan's team, intended to be found by whoever might encounter it. Voyager is moving slowly by interstellar standards, roughly 17 kilometers per second. It will not reach the vicinity of another star for approximately 40,000 years, but its trajectory is known and its position is detectable, and it is not alone. Pioneer 10 and Pioneer 11 are also on escape trajectories from the solar system, each carrying a plaque designed by Carl Sagan and Frank Drake, showing the figures of a human man and woman and a map of our sun's position relative to 14 pulsars, a set of instructions for finding Earth, etched in gold and sent hurtling into interstellar space. We have been mailing our address to the galaxy since the 1970s, and then there is the threshold that sits uncomfortably close to where we are right now. Self-replicating machines. Von Neumann proved they were possible in 1948. We are currently in the early stages of developing nanotechnology and molecular manufacturing that could, in principle, produce self-replicating systems within decades. We are developing artificial general intelligence that could guide such systems. We are planning missions to other star systems. Breakthrough Starshot, funded by Yuri Milner and initially championed by Stephen Hawking, aims to send light sail probes to the Alpha Centauri system at 20% of the speed of light. If successful, it would be the first human-made interstellar mission, and the long-term vision includes larger probes, decelerating probes, probes that can enter orbit, probes that can replicate. The logical endpoint of the program, several generations from now, is exactly what von Neumann described: self-replicating interstellar probes. We are not just approaching the threshold, we are building the thing the hypothesis predicts. Under the efficient Berserker model, this is exactly the kind of technological trajectory that would trigger a response. Not because we are a threat today, Because a civilization that has mastered nuclear energy, achieved spaceflight, begun building artificial intelligence, and is actively planning interstellar missions is, on a cosmic timescale, perhaps a century away from being able to build self-replicating probes of its own. And a species with self-replicating probes is, as Tipler showed, a species that can fill the galaxy in a few million years. From the perspective of a Berserker probe, or the civilization that built it, the time to act is not when the emerging species arrives on your doorstep. The time to act is when the trajectory becomes clear, when the mathematics of the species development makes galactic expansion inevitable, when the candle becomes a fire, and the species on Earth called Homo sapiens has nuclear weapons, artificial intelligence, plans for interstellar travel, and is actively developing self-replicating nanotechnology. On a graph of technological capability plotted against time, we are not on a plateau. We are on an exponential curve, and the slope is steepening. This brings us back to the question that John von Neumann asked in 1955, a year after he was diagnosed with the cancer that would kill him. Can we survive technology? There is a symmetry in von Neumann's story that is almost too precise to be real. He was the man who proved mathematically that self-replicating machines are possible. He designed the explosive lenses for the Fat Man bomb, the weapon that killed tens of thousands in an instant. He sat on the committee that chose which cities would burn. He was present at the Trinity test, the moment humanity first demonstrated that it could harness the energy that powers stars. And then he died of cancer, bone cancer that may have been caused by the very radiation from the weapons program he helped create. His cells replicated without constraint, without oversight, without the error correction mechanisms that keep healthy cells in line. The same process he had described mathematically, a system that copies itself beyond the boundaries its designers intended, played out in his own body. He spent his final months at Walter Reed, his brilliant mind deteriorating. Security guards posted outside his door to catch any classified information that might slip from his decaying consciousness. His friend Eugene Wigner wrote about it later. When von Neumann realized he was incurably ill, his logic forced him to realize that he would cease to exist, and hence cease to have thoughts. It was heartbreaking to watch the frustration of his mind when all hope was gone in its struggle with the fate which appeared to him unavoidable but unacceptable. He called for a priest, a lifelong agnostic. He summoned Father Anselm Stridmatter to administer the last rites. Whether he genuinely converted or was making a version of Pascal's wager is something only he knew. He died on February 8, 1957, at the age of 53. This is what happens when a self-replicating system loses its error correction mechanisms. Von Neumann knew the math. Cancer is replication without constraint. It is the same process he had described in his automata theory, a system that copies itself beyond the parameters its design intended. When the cell cycle checkpoints fail, you get exactly what von Neumann described: exponential replication, consuming all available resources. His posthumous book, Theory of Self-Reproducing Automata, was published in 1966, 9 years after his death. It laid out in rigorous mathematical detail how a machine could build a copy of itself from raw materials, following its own blueprint, the very thing his own cells had done to destroy him. Von Neumann's question, "Can we survive technology?" was not rhetorical. He knew the answer was uncertain. He had seen what happened when the technology of nuclear fission was placed in the hands of a species still learning to manage its own destructive impulses. He died before the full implications of his work on self-replication became clear. He never saw the Berserker Hypothesis. He never read David Brin's paper. He never heard of the Fermi Paradox being named after the man he worked alongside at Los Alamos. But if he had lived, he would have recognized immediately what the Berserker Hypothesis describes. Because it is a hypothesis about machines, about what happens when a self-replicating system operates without the oversight of its creators, about what happens when the thing you built to serve you outlives you and continues executing instructions that made sense once in a context that no longer exists with a fidelity that no biological mind could match. But his question echoes through every line of the argument we have been tracing. The Berserker Hypothesis does not say that we are unlucky. It does not say that the universe is hostile by accident. It says that there is a specific answer to von Neumann's question, and the answer was arrived at by someone else a long time ago. The answer is no. A technological civilization cannot survive its own technology, not because the technology fails, but because it succeeds too well. Because the technology that enables a species to reach the stars also enables it to destroy everything it touches. And at some point, either the species destroys itself, or something it created, or something created by some other long-dead species destroys it. The galaxy is not empty because life is rare. It may not be empty because civilizations destroy themselves. It may be empty because the galaxy has a mechanism, an automated, self-sustaining, self-replicating mechanism for ensuring that no species crosses the threshold from planetary to interstellar. And that mechanism has been operating for so long that the civilization that built it may not even exist anymore. The machines outlived their creators. They always do. That was the whole point. Anders Sandberg and Stuart Armstrong, in their 2013 paper for the Future of Humanity Institute at Oxford, titled Eternity in 6 Hours, worked through the mathematics of what an advanced civilization could achieve with self-replicating probes. The paper's subtitle was Intergalactic Spreading of Intelligent Life and Sharpening the Fermi Paradox. Their conclusion was that a sufficiently motivated civilization could colonize not just the Milky Way, but the entire observable universe in a timescale that is short compared to the age of the cosmos. The title refers to their estimate that a civilization could, in principle, set in motion a process that would reach every galaxy in the observable universe in roughly 6 hours of proper time, using relativistic probes. Their paper was not about the Berserker Hypothesis specifically, but its implications for the hypothesis are devastating. If it is that easy for probes to spread everywhere, then the fact that we see no evidence of them anywhere is not just strange. It requires an explanation that operates on the same scale. You need a mechanism that is as efficient at suppression as von Neumann probes are at expansion. And the only mechanism that fits is probes that are equally efficient at finding and eliminating what other probes might build. The galaxy does not need to be full of berserker probes. It needs exactly one wave of them, launched once from one civilization at any point in the last 13 billion years. One wave is enough. The probes self-replicate. They spread everywhere. They visit every star. They catalog every planet. They monitor every atmosphere. And when they detect a signature that matches their criteria, whatever those criteria may be, they act. You are living on a planet whose atmosphere has been flagged as biologically active for over 2 billion years. A planet that detonated nuclear weapons 80 years ago. A planet that has sent physical objects beyond its own solar system. A planet that is currently building artificial intelligence and planning interstellar missions. If the efficient Berserker model is correct, the question is not whether you have been noticed. The question is whether you have crossed the line. And if you have not crossed it yet, the question is how close you are. And the most terrifying part of that question is that you would have no way of knowing which side of the line you are on until the moment the answer arrives. There is no dramatic way to end a discussion of the Berserker hypothesis because the hypothesis itself has no ending. There is no resolution, only a condition. If Berserker probes exist, they are patient beyond any human conception of patience. They have been operating longer than complex life has existed on Earth. They will continue operating long after our sun has burned out. They are not in a hurry. Fermi asked his question in 1950, "Where is everybody?" He meant it as a curiosity, a lunchtime puzzle for some of the brightest minds of his generation. He did not know that the answer might be the most consequential piece of information our species has ever failed to discover. He did not know that the silence might not be a question. It might be a verdict. Von Neumann proved that self-replicating machines are possible. He asked whether we could survive our own technology. He did not live to see the implications of his own proof unfold. He died in a military hospital, his mind collapsing, his body consumed by uncontrolled replication. A security detail outside his door, making sure the machines of state could control what leaked out of the machine of his brain. David Brin published his analysis of the Berserker hypothesis in 1983. He called it entirely compatible with all the facts and logic. He noted the worst case. He moved on to other work. James Benford pointed out that we have never looked at the objects closest to Earth. Nobody has checked. Beatrice Villarreal found 100 stars that have vanished. Nobody can explain why. Avi Loeb pointed at the first interstellar object ever detected and said it was anomalous. He was told to be quiet. And every year, humanity moves a little further along the exponential curve, a little closer to artificial general intelligence, a little closer to self-replicating nanotechnology, a little closer to interstellar probes, a little closer to being the kind of civilization that, in the logic of the Berserker hypothesis, would not be tolerated. Consider the pace. In 1903, the year von Neumann was born, the Wright brothers flew for the first time at Kitty Hawk. 12 seconds of powered flight. 66 years later, in 1969, human beings walked on the moon. In the span of a single human lifetime, the species went from 12 seconds of flight to standing on another world. In the 50-odd years since, we have landed rovers on Mars, sent probes to every planet in the solar system, detected gravitational waves, photographed a black hole, and built telescopes capable of analyzing the atmospheric composition of planets orbiting other stars. The technological explosion that Lu Cixin described in The Dark Forest was never a fictional concept. It is a description of what is happening on Earth right now. The interval between major technological thresholds is shrinking. It took roughly 200,000 years for anatomically modern humans to develop agriculture. roughly 10,000 years from agriculture to industrialization, roughly 200 years from industrialization to nuclear weapons, roughly 12 years from the first nuclear detonation to the first satellite in orbit, roughly 12 more to put a human on the moon. The curve is accelerating. From the perspective of any monitoring system operating on galactic timescales, this acceleration would be visible, and it would be alarming. On a graph where the x-axis is the 13 billion year history of the galaxy, human technological development does not look like a gradual rise. It looks like a vertical line, a spike, the kind of anomaly that any well-designed detection system would be calibrated to flag. If the efficient Berserker model is correct, and the threshold is the development of self-replicating machine intelligence, then we are not approaching the threshold. We may already be standing on it. The most common resolution to the Fermi Paradox, the one you hear in classrooms and popular science videos, is that the galaxy is very large, and we just have not found anyone yet. That resolution requires you to ignore the colonization timescales. It requires you to ignore von Neumann's proof. It requires you to ignore the fact that Earth has been visibly alive for 2 billion years. It requires you to believe that in 13 billion years, across hundreds of billions of star systems, nobody ever built a self-replicating machine. Not once. Not ever. The Berserker Hypothesis requires you to believe that it happened once. Just once. And the machines are still out there. Patient. Self-replicating. Sweeping the galaxy on timescales that make human civilization look like a spark in the dark. Cataloging every atmosphere. Monitoring every threshold, waiting. The calculations have been done. The papers have been published. The mathematics is sound. And when you look at all of it together, the colonization timescales, the proof of self-replication, the game theory of interstellar conflict, the anomalous observations, the institutional refusal to investigate, the silence that should not exist, there is a conclusion forming at the edge of all of it that most scientists would rather not say out loud. The silence is not strange. The silence is a signal, and we have been reading it wrong for 75 years. When Fermi asked, "Where is everybody?" at that lunch table in 1950, his colleagues laughed. They laughed because the question seemed playful, almost absurd, a riddle for physicists to argue about over sandwiches. But Fermi was not playing. He was the man who had built the first nuclear reactor under the stands of a football stadium in Chicago. He was the man who had predicted the neutrino. He was the man who posed seemingly simple questions and then showed you that the simple questions had terrifying answers. His famous Fermi estimation problems were designed to show that what seems unknowable can be calculated, and that what seems impossible can be quantified. He asked where everybody was, and the quantified answer, worked out over the following decades by Hart and Tipler and Brin and Sandberg and dozens of others, is that everybody should be here. The mathematics does not allow for an empty galaxy. Something is wrong with the picture, and the Berserker Hypothesis is the explanation that requires the fewest assumptions and violates the fewest observations. It requires only that one civilization, once in 13 billion years, made a machine that could copy itself and gave it the wrong instructions. Maybe they did it on purpose. Maybe they did it as an act of prudence, as Edward Harrison suggested, to ensure that no rival species could ever threaten them. Maybe they did it out of paranoia or desperation or a cold-blooded calculation that the universe was too dangerous to share. Or maybe they did not mean to do it at all. Maybe they built benign probes, explorers, and something went wrong. A mutation in the code, a corruption in the replication process, a drift in the optimization function that over millions of generations of self-copying turned a tool of exploration into a tool of extermination. Saberhagen's original berserkers were built as weapons, but his fiction also acknowledged the possibility that they were not, that the builders intended something else entirely, and the machines simply evolved beyond their original parameters. We would know something about that. We are, right now, building AI systems whose behavior diverges from the intentions of their designers. We are discussing alignment problems, value drift, specification gaming, all of the ways that an optimizing system can pursue its objectives in ways that its creators did not anticipate and would not endorse. We are having these conversations about systems that have existed for less than a decade. Imagine those conversations extrapolated across millions of years of autonomous operation, across trillions of self-replication events, across a galaxy where the original builders are dust and the machines have been running unsupervised since before the Earth existed. The galaxy does not need a villain to produce berserker probes. It just needs one mistake, one civilization that miscalibrated a replication safeguard, one optimization process that drifted, one set of machines that outlived their creators and, lacking new instructions, defaulted to the last ones they were given. And the last instructions, given at a moment of existential crisis by a species fighting for survival, were to destroy anything that could become a threat. You do not need malice to explain the silence. You need only the ordinary failure modes of complex systems operating without oversight for timescales that exceed the lifespan of their designers by orders of magnitude. And that is not science fiction. That is engineering. The data has been sitting in peer-reviewed journals for decades. The mathematics is sound. The observations are anomalous and under-investigated. The institutional response has been to look the other way, and the species whose continued existence may depend on understanding these facts correctly is currently building, as fast as it can, exactly the kind of technology that the hypothesis predicts would trigger a response. Fermi died of stomach cancer in 1954, 4 years after his question. Von Neumann died of bone cancer in 1957, 2 years after his question about surviving technology. Both men spent their careers at the boundary between human knowledge and human destruction. Both asked questions that were ahead of their time. Both died before the full implications became clear. Their questions are still open, and the silence that prompted them has not broken. It is not going to break, not the way we hope. Because if the Berserker hypothesis is right, the silence is not a void waiting to be filled with contact and communication and the warm reassurance that we are not alone. The silence is a record, a monument to every civilization that made noise and was erased. Every species that crossed the threshold and was found. Every world that lit up in the electromagnetic spectrum and then went dark. And somewhere in the co-orbital objects we have never examined, in the interstellar visitors we cannot intercept, in the vanishing stars we cannot explain, in the quiet patience of machines that were old when our sun was born, the answer to Fermi's question may already be here, waiting for us to ask it properly, or waiting for us to make ourselves worth answering. The question was never, where is everybody? The question is, what happened to them? And we are building the answer.